Yeah, so thanks a lot for the invitation to this really inspiring meeting. And thanks to Stephen for giving an optimal introduction into the treatment of chronic viral infections, which has, I think, quite a few different challenges from what we've heard before. The main one being that there is treatments which control the disease. And of course, the burden or the demand for high safety of a product is higher than if you have a devastating disease. Now, we work on CAR T cells already for quite a while, starting when I was still in Cologne, working together, or when I met Chimeric Antigen there. Now, let me present where we stand at the moment. So just some background to hepatitis B virus infection. Hepatitis B virus infection can basically have two fates. It can either be self-limiting, that's accompanied by a broad and strong T-cell response, or it can be persistent, mainly if you acquire the disease as a young child, and then there is basically almost no detectable T-cell response. That's very different from HIV, where you always can detect T-cells. In HPV, you cannot. So the idea of adoptively transferring T-cells came in, and there were early studies with stem cell transplants of vaccinated individuals, and that showed that was safe and the recipients could be cured from HPV. So that's the basic idea. Now you could ask, is there a clinical need? And I would argue, yes, there is a clinical need, because there's a very high number of people who carry HPV. It even went up in the last reports to 296 million, so almost 300 million carriers, and the death toll is more than 800,000 per year. Obviously, there is a different distribution around the world, very little in the US. That's why for a long time there was not a lot of interest, but still, even in the US, the numbers are high. And the death toll, if you compare that to the death toll of other major infectious diseases, it overcame the death toll for HIV, it overcame the death toll for malaria, and it even in the recent years reaches the level of the death toll for tuberculosis. Now there is, why is that? Because in particular hepatitis B, which is the major cause of this, of the death toll, or the major reason, it has very mild symptoms for a long time. And then patients may develop liver cirrhosis. But more severely, some of them right away develop hepatocellular carcinoma. And that's, of course, then with the age of 35 or 40, and that's very unfortunate, not only for the person, but also very often for the families. Now, what does hepatitis B virus do? Hepatitis B virus deposits a persistence form, the so-called cccDNA, in the nucleus of infected cells as an episome. This then produces viral antigens and virus. The virus production you can block if you use nucleoside analogs or other antivirals. But the antigen production, S antigen production, goes on. And what over time also happens is that the virus integrates. This does then not give rise to any infectious virus anymore, but it still causes the, somehow I cannot use this here, it still causes the secretion of S antigen, and that's why we think that's the ideal target, because you could target cells with integrates, which are the precursors of hepatocellular carcinoma, as well as the infected cells. And then, of course, we wondered, okay, how frequently do we detect that in hepatocellular carcinoma? And if that's a carcinoma based on HPV infection, then you can see quite a lot of staining, of cells staining positive. And we also looked whether the S antigen would be detected on the surface of infected cells, so whether you can use that as a target for a CAR. And we found, yes, it is. It's already, I think, somewhat indicated by those stainings here, but it becomes obvious when you then stain cells with integrates and you see on the surface of the replicating cells you have the target, the S antigen. That was quite nice, but to develop that into a CAR, we needed a binder. And in my time back in Heidelberg, working with Heinz Schaller, we had identified a single chain antibody fragment, which was quite able to bind not only virus or bound coded S antigen, but also cells. So we took that, characterized that a little more in detail, and we found that it's able to bind all the different known HBV genotypes. Very nice, because that would give you a target for basically everybody throughout the world who's virus positive. And then we use that to do EM stainings and look at whether really cells which are infected or carry the integrate, whether these antibody or the single chain fragment transformed into an antibody would target the cells. And these are cells which carry an integrate, and this is cells which have been infected with the virus. And when you go in, then you may appreciate the antibody binds to the surface of the cells with integrates, but also of the cells which carry the virus after infection, but not to the background cells. So, okay, we thought that seems to be a suitable binder, potentially broadly applicable. Then, of course, we had to address the question whether our CAR T-cell, our CARs, which we designed together with Chimeric Antigen, it's a second-generation CAR in that case, whether they would really target the cell where there is no antigen secreted, so no antigen could just bind back to the cell surface as a target. And to do that, we made constructs where we expressed the S protein from an L expression vector and knocked out the start codon, so that the S domain is still there as a target, but it's not secreted anymore. And that works. You can see here, no secretion, but quite significant secretion if you use only the S domain. And now, whoops, now looking at effectivity of our CARs, we transfected HEH7 cells, that's cancer cells, with our different constructs. And as you may appreciate, all the constructs are targeted by our CARs, meaning that also that one which does not secrete the S is targeted and activates the CAR T cells. So that seems a suitable approach. Now, even a little earlier, when we had worked together with Heinrich, we tested our CARs in a setting of primary hepatocytes. And we were lucky to be able to work together with surgeons who could provide us with tissue resectates from metastases, usually bowel cancer metastases, and we could isolate primary hepatocytes out of the healthy tissue around this metastasis. And we could either infect them with HBV or not infect them. And we got PBMC from the very same patients, and these we could graft with our CARs. And what we found is that the CAR targeting S is activating. Also, one targeting the L protein is activated, but not the control CAR, and only in cells which carry HBV, but not the ones next here which do not carry HBV. And they secrete IL-10, they secrete, interferon gamma, they secrete IL-2, and most importantly, they eliminated the CCC DNA to at least a level which was completely undetectable in cell culture. So really, those CARs seem to be able to do an HBV cure. Now we wanted to know what's the mechanism. Is that purely cytotoxicity, or is there also cytokine-mediated effects? And we took those CARs into a setup where we had either mock cells or cells which were infected with HBV and treated with T-cell cytokines, or we co-cultured them with our CARs. And to be able to see what the non-cytotoxic effect is, so the effect which only comes from the cytokines, we separated the CAR T cells from the target cells by a transwell, and either stimulated them or did not stimulate them on the transwell. And the outcome was that the cytokines have a role, the co-culture, of course, because there the target cells are killed, But also when you have the CAR T cells on a transwell and stimulate them, you find an anti-HBV activity. And that means the redirected T cells, the CAR T cells, they could act in a cytolytic fashion, but also in a non-cytolytic fashion by secreting cytokines. Now, that for us meant there is two potential targets, disease targets. The one is the hepatocellular carcinoma, which carries an HBV integrate. There, the killing obviously is important because you have to kill the cancer cells, but also the cytokine secretion would modify your tumor microenvironment and hopefully lead to some activation of T cells against the different tumor antigens. And then there is the HBV situation, infection situation, where the T cells would target the cccDNA, so the persistence form or cells which carry that, and that would, of course, could also be done by killing infected cells, but there would be an important role also by T cell cytokines contributing in non-cytolytic depletion of the cells. So these two mechanisms. And that then brought us to the idea, okay, we could go into cancer cells or into cancer patients, so patients which carry hepatocellular carcinoma on the basis of HBV, and on most times they still have liver cells which are infected, so we would also see whether the treatment is safe in the situation of an infection. And this could be done either by TCR-Ts or CAR-Ts or even by T-cell engager antibodies. I will not go to. So the obvious advantage for CAR is that it's independent of the MHC type. Working with TCRs, you have to be very selective for your target population, plus the TCR-Ts in our hands often also in their activity depend on the virus genotype. So that makes it quite complicated to pre-select the patients. Obviously, the CAR has no TCR mispairing, and it should work independent of antigen processing. The disadvantage, however, is if you work with an infectious disease, you will have virus that is secreted, and the target will also be on the viral or subviral particles in the serum, and that could either overactivate or inactivate your CARs. So that's something one also has to take into account. And the antigen load, in general, you need for activation of a CAR T cell is higher than the one you need for a TCR T cell. Now, to see whether that would work in vivo then, where we have everything around, where we have the secreted antigen or the secreted virus and subviral particles, and could also observe potential toxicity, we went into HBV transgenic mice. And in a first study, what we found is that the IV-injected CAR T cells, they target the liver and they accumulate in the liver, in the vicinity of vessels. They caused an ALT increase, ALT rise, which is an indication that liver cells die, but it was very transient. So at day 12 already, the ALT was almost normal. And we did a control in there with a different CAR, a CAA CAR, but also a signaling deficient CAR to just see whether the effect would also occur when the CAR potentially captures the virus or something like that. But when we looked at the outcome, then the two controls did not do anything, but our CAR continuously reduced the numbers of viruses in the periphery and the numbers of positive cells in the liver. Now, that's a transgenic mouse, obviously. Every cell carries the virus, so it will always come back. Plus, we observed that there is some immunity against the CAR in these mice, but still the effect was quite impressive, taking into account that really every liver cell is a target. We saw that our CAR, the CAR, really reduces largely the number of HBV DNA overall in the liver. And the mice were quite healthy, so we didn't see any severe side effects, so we didn't have to take them, any one of the mice out of the experiment because they lost too much weight or something like that. So SCAR T cells infiltrate the liver, kill hepatocytes, and block HBV replication. However, we wanted to go a little deeper and also do more long-term experiments, and then we had hit the problem that the mice raised an immune response against our fully human CAR. Now, what we then did is we did an experiment where we irradiated the mice, a little similar to lymphodepletion, and then transferred a delta, so a signaling deficient CAR T cell, and afterwards we transferred our SCAR T cells into the mice. And then we looked what happens, and the transduced cells, they persisted very well in the mice which had been irradiated before, but they were relatively rapidly lost in the mice where we did not do the irradiation before. And looking at the antiviral effects, it's also very obvious that the group which received the pretreatment where the T cells persisted, they had a constant drop in S antigen and also E antigen, indicating that they were on the way of controlling or maybe even curing the virus. So they persist if they have the good conditions and they have long-lasting antiviral activity. Now, having these results in hand, we thought, okay, it would be the time to maybe go into humans. And I co-founded a company in 2018, which is in Singapore and runs clinical trials in China. And this is the results of an IIT, not with CARs yet, but with a TCR-T. We also in parallel identify TCRs. And what you can see here, or may appreciate here, is that most of the patients, they really, upon injection of the TCR-Ts, which we gave either in a dose of 5 times 10 up to the 7 or 1 time 10 up to the 8 per kilogram, that they drop their S antigen significantly, meaning there is definitely an on-target activity. In one patient, we did not see a sustained drop of S antigen, and that's what we're trying to understand, why 80% of the patients, that's a low number. Yeah, 5 out of 6 patients responded, but the one didn't. And this was always accompanied by, by a rise in ALT, which then went in parallel with a drop of S antigen, except in that one case, that patient also had a rise in ALT, but did not respond, but all the others had a rise in ALT and responded with a drop of S antigen. This ALT rise was quite transient, meaning that the liver microenvironment, which is like an immunotolerant microenvironment, sort of also mitigates the TCR T cell function. And now you may wonder, what does the liver look like? And that's stainings. So that's staining from one patient before the therapy, and in brownish you see, in that case, core protein staining of the virus, and that's after therapy, and there is basically no positive cells you can detect anymore. So quite sure the TCR-Ts have either fully or at least almost cured the infection. Did they also do something for the tumor? And the answer is yes. In the patients which responded with an antiviral response, there was also a tumor response. In red here you see the patients which have received more than 1 log as antigen reduction, and these two had less than 1 log. And there is really the progress-free survival of the patients is really different. It's better in the patients which have an antiviral response. One has to take into account this is very terminal patients. They usually have already received and failed 3 prior anti-cancer therapies. So it's really hard to treat them, but I think for that situation, the results are quite encouraging. Okay, let's go back to CARs. Now, we had this first CAR, but we noticed that that has some tonic signaling, and some off-target effects. So we thought, okay, we'll need better CARs. So what we did then is we started isolate human monoclonal antibodies in a single cell approach, sorting the B cells for S antigen positivity, using two different colors, and identified a set of clones, two of which were the most promising, and that's here shown, the 4006 and the 4008, which secreted quite nice amounts of anti-S antibodies. And these antibodies, when cloned and expressed recombinantly, they showed a very nice affinity in the nanomolar range. So we thought, okay, that might be interesting antibodies to be transformed into a CAR. And we did that and then tested, first we tested whether they also would address all the different HPV genotypes to be able not to treat everybody, irrespective of the virus infection or the virus genotype. And both of them do. That's shown here. That's all the different genotypes circulating in the world. 4006 has a little higher affinity than 4008 has, but both definitely are broadly neutralizing. So we transformed them into CARs, this time working together with Stan Riddell in a little more up-to-date format of the CARs, and showed that they were expressed on T cells. So our original CAR transformed into that format, and the 4006 and the 4008. And they also showed high affinity or avidity to, in that case, bound S antigen. And the two new CARs even showed a higher avidity than our old C8 CAR shown in red here. And then we tested them, obviously, in cells. And what we found is that the original CAR which we had, the C8 CAR, does this cancer cells, HepG2 cells, without an antigen. They showed a tonic signaling and expressed interferon gamma if the E to T ratio was high. And also the 4006 does that. But the 4008 CAR showed no basal activity without antigen presence. And that's then, but very comparable activity if the antigen is present to the other two. This is a dilution series of effector to target ratios. So this one looked very promising. We also saw the same if we looked at proliferation, and the 4008 looked much better. And also when we checked cytotoxicity in an excelligence assay, in that case, we saw that on non-antigen carrying cells, there is a certain activity of the C8 CAR and the 4006 CAR, but none of this the 4008 CAR. Also, all of the CARs, if the antigen is present, are similarly effective. So we think one interesting thing is that really the binder seems to be able to determine whether there is unwanted tonic signaling, and we think we have an interesting novel CAR to test. Now, I hope I could convince you that T cells can be retargeted to HPV-infected cells using either TCRs or CARs, that HBs antigen is a suitable target expressed on the surface of HPV-positive cells, being that infected or tumor cells, that redirected T cells kill HPV-infected cells and also HBs antigen-positive hepatoma cells, that they also have a non-cytolytic antiviral activity, which adds on to the cytotoxic activity. We have first-in-man data. They still are preliminary, obviously, and a systematic IND is running. And that showed that the redirected T cells are safe, and they reduce S antigen, but also the load of the cancer. And improved CARs hopefully offer the opportunity for clinical evaluation, then being more broadly applicable and easier than TCRTs. And with that, I'm at the end. And thank you very much for the attention, but I also want to acknowledge all our collaborators, the people who did the work in the lab. It's really a great lab, the former members, and our collaborators at different institutions, and also the funders, obviously. Thank you.